Welcome to the second to last lecture of the second iteration of the Plutus Pioneer Program. This lecture is not about Plutus, but about Marlowe, which is a domain-specific language for financial contracts built on top of Plutus. And even though Marlowe has also changed a little bit since the recording of this lecture for the first iteration, the changes are much smaller than those that happen in Plutus all the time. So I decided to not update or edit this lecture because I think it's still mostly accurate, and in particular the demo at the end still works. In the previous lectures we have learned about all the important ingredients for writing a Plutus application. We have first looked at the extended UTXO model, the accounting model that Cardano uses, and the addition that Plutus brings to it. Then we have talked about on-chain validation, about minting policies, about writing off-chain code. We have seen how to deploy smart contracts and also how to test them. And Plutus is a very powerful language, so powerful in fact that you can implement other languages on top of it. So you can write an interpreter in Plutus for other languages. And one such language is Marlowe, which is a so-called DSL, domain-specific language for financial contracts. And because this is the second to last lecture of this course, I thought we should do something special, so I invited Professor Simon Thompson, who is a very prominent figure in the Haskell community and who leads the Marlowe team, and one of his colleagues, Alex Nemish, to give guest lectures and tell us a bit about Marlowe in this lecture. And afterwards, I will do a small demo of the Marlowe Playground and demonstrate playing with a simple Marlowe contract.
Hi, I'm Simon Thompson from the Marlowe team, and we're here this afternoon to give you an introduction to Marlowe. Let's get started. So Marlowe is a special purpose language for writing financial contracts on Cardano. Now, why do we build special purpose languages, or sometimes we call them domain-specific languages? Well, one reason is that we want to build languages that are closer to the language of the user and not so much the language of the system. So they're designed to be in the specific domain of the application. So a financial language will talk about payments, for example. And when we write a special purpose language, we get some advantages. We can write down things in that domain, but we can't perhaps write as much as we could in a general purpose language. And if we do work in this more specialized context, we have the advantage of being able to give people better feedback, better error messages, but also we can give more guarantees on program behavior. And that's one of the things I'm going to stress in this lecture. Okay, what sort of assurance can we give? I mean, we can give two kinds of assurance, really. We can make sure that contracts do what they're supposed to do, great, but we can also make sure they don't do what they shouldn't. And we'll see both aspects of that as we go along. We've designed the language to be as simple as it can be, and the implementation reflects that. I'll talk a bit about that in some more detail later on. Contracts are nice and readable, and also we can easily simulate them. And so we can present to users a very clear picture about how their contracts in Marlowe will behave. And in fact, we can do more than that. Because they're particularly restricted, we can, before a contract is executed, actually explore every possible behavior path it can take. So we can give complete guarantees about how a contract will behave, not just on one or two tests, but on every possible execution sequence. And also it's more straightforward to actually write mathematical proofs of various kinds of safety. So that's, if you like, the strongest criterion that we can hit in this kind of world, that we have a mathematical proof that the system will do certain things, won't do others. Okay, but let's start by asking the question, what does a financial contract do? And let's step back from what we see so what can a contract do? Well, let's take a look at what various things a contract can engage in. It can accept payments from participants in the contract. And according to choices perhaps made by one of the participants, it can evolve in different directions. Do I sell or do I stick with the contract, for example? Or it can make decisions based on external information, such as the information coming from an exchange, a stock exchange or a currency exchange, for example. So information coming from an oracle can determine the future behaviour of a contract. And finally, the contract can also make payments out. If money has been deposited in the contract, it can also make payments out to participants. So we have payments, flows of money, we have choices according to external factors. And one final thing that we have, that the roles in a contract are themselves things that can be owned. So we represent that in Cardano, in Marlowe, by minting tokens that represent those roles. Now, that means that we can use those tokens as evidence that somebody is meant to be playing a role. So they're a form of security, of validation that the person submitting a particular transaction is meant to be able to submit that transaction. It fits with their role. But also it means that these roles can become themselves tradable. So we can trade roles in a running contract. I could transfer a role in a contract that I have to you, perhaps for some money, or indeed that role could be that token could be traded by another Marlowe contract or a Plutus contract. So we use native tokens to represent roles in contracts. So we have roles, we have payments, we have external choices, external information coming in through oracles. So those are the general ingredients. Now let's think about how to design a language based on those ingredients. And remember, when we design a language of contracts, what we're really doing is designing a programming language. A contract is just a smart contract, is just a program running on a blockchain. So a contract in principle could run forever. And also more subtly, it could, for example, just get stuck waiting for an input forever. If it's waiting for me to make a choice, it could potentially wait forever. It could also, as a program holding assets, it could terminate holding on to those assets. So it could lock up those assets forever. And potentially it could double spend, I guess. In principle, a program could try and do that. So there's a whole lot of security issues that a program might have. A contract might have. So what we chose to do was design for safety. So we designed, first of all, for contracts to be finite. Their life will be finite. There is no recursion or loops in Marlowe. We'll come back to that a bit later on when we talk about Marlowe being embedded in other languages. But Marlowe contracts themselves are finite. Moreover, we can be sure that contracts will terminate, and we do that by putting timeouts on every external action. Every choice or deposit of money into the contract comes with a deadline, comes with a timeout. And so Marlowe contracts cannot wait forever for somebody to make a choice, for an action to happen. If you hit the timeout, then an alternative course is taken. And reading from a contract, because we have these timeouts in the contract, each Marlowe contract will have a defined lifetime. We can read that off from the timeouts. So we have a very clear constraint on what we can do, but that gives us safety built in. And finally, we've designed the semantics of the language so that when a contract reaches its close at the end of its lifetime, any money left in the contract will be refunded to participants. So we've built into the semantics, into the way the language is defined, that no money is retained when things terminate. So we've got those safety properties. Your money is always only going to be committed for a finite length of time. It will always, if money is not spent by the contract, it will be returned to its rightful owner. Now, conservation of value is something that we get really for free from the underlying blockchain. We can't, the underlying blockchain guarantees double spend, and because we're using the transaction mechanisms of the underlying blockchain, we can be sure that we are getting conservation of value. Okay, so that's giving us a whole lot of guarantees just out of the box. And these are not guarantees that there are for Plutus contracts in general. In general, a Plutus contract could go on forever, it need not terminate, and it could terminate with having control of a whole collection of assets which are then become unreachable. Okay, so those, just to stress, these properties I'm highlighting here are safety properties, are assurances that we can give to Marlowe users. Now, what does the language look like? Let's cut to the chase. So Marlowe is, at heart, it's represented as a Haskell data type. And you can think of, I'm sure you're familiar with data types in Haskell. Data types in Haskell we can think of as syntax of simple languages. And let me just talk you through the constructs that we have in the language. We have a pay construct, and in that, a party, one of the parties in the contract, makes a payment to a payee of a particular value, and then the contract continues with what we call the continuation contract. We can go in two separate directions. We can observe whether or not a particular observation is true or not. If the observation is true, we follow the first contract. If the observation is false, we follow the second. So, simple payment and then a simple conditional. The most complex construct in Marlowe is the when construct. And you can see it takes three arguments. And the first of those is a list of action contract pairs, a list of cases. And let's look at what that list represents. Let's think what it represents. What the when construct does is wait for one of a number of actions. And when one of those actions happens, it performs the corresponding contract. So it could be waiting for a deposit, which if I have a case where the first part of the case pair is a deposit, then we will execute the corresponding second part. Similarly with making a choice. Similarly with getting a value from an oracle. So here we're waiting for external actions, and of course the contract can't make those actions happen. A contract can't force somebody to make a choice. It can't force somebody to make a deposit. But what we can do is say, well, if none of these actions takes place, no action taken place, no corresponding contract, we will hit the timeout. And when we hit the timeout, what we'll do is perform this contract. So we can guarantee that something will happen in this construct, either because one of the actions triggering a successive contract, or we simply hit the timeout and go to that continuation. So we know by the time we hit the timeout, something will have happened. We can't sit there waiting forever. And then finally we have the close, which has the semantics defined so that nothing is retained when we close. So there is the Marlowe language. a very simple set of constructs. But we'll see that we can use those in a variety of different ways, that we can construct Marlowe contracts in a variety of different ways. Okay, so there's the language. What is the Marlowe product itself? Well, what we have is a suite of things. And what I'm describing here is the overall vision for Marlowe. And I'm going to describe that and then tell you where we are with fulfilling that. So at the moment, what we have is, you might have seen, and I'm going to show you a demo shortly. We have a prototype for Marlowe Run, and that is the system through which an end user will interact with contracts running on the Cardano blockchain. So if you like, Marlowe Run is the Marlowe dApp. It's the thing that allows Marlowe contracts to be executed. We're also building a market where contracts can be uploaded, downloaded, and where we can provide various kinds of assurance about those contracts. We allow contracts to be simulated interactively, and we call that Marlowe Play, and we allow contracts to be built in various different ways, and we call that Marlowe Build. Now, in fact, what we've done at the moment is bundle those two, Marlowe Play and Build, into what we call the Marlowe Playground. So as things stand at the moment, you can, it's been available for a while, use the Marlowe Playground to simulate and construct Marlowe contracts. We're in the process of redesigning the user interface of that, the user experience, on the basis of what we've done with Marlowe Run. So we're able to build and simulate Marlowe contracts. What we're releasing very shortly is the prototype of Marlowe Run, and this is the prototype of how end users will interact with Marlowe on the blockchain. And our intention is that we'll have all these products available when running on the Cardano blockchain, when we have the full support for this on Cardano, which will involve having the Plutus application backend and wallet backend and so on working as they should. Okay. Now what I'm going to do now is just take a short break and show you a demo of what we have in Marlowe Run to give you a sense of what we can do with at the moment with giving users the experience that they will have when Marlowe is running on blockchain. This will be the app that is going to provide that experience. At the moment it's running locally. We will in a few weeks' time be releasing a version that runs in a distributed fashion on a simulated blockchain, and then as we go into the end of the year, we expect to have this running for real on the Cardano blockchain itself. So let's go to the demo now. Marlowe Run runs in the browser, and what it does is provide the end user interaction with contracts running on the blockchain. For the moment, we're simulating that blockchain inside the browser, but eventually this will be the tool you'll use to run contracts for real on Cardano. Now, to interact with the contract, your wallet needs to be involved to control your signature and to control your assets. So we link up Marlowe Run with a wallet. Let's link it up with Shruti's wallet. So in this window, we see the world from Shruti's perspective. And let's open up another window and link in that window the world with Charles's perspective. And at the moment, neither of them has any contracts running. They have a blank space there. But let's start a contract up. Let's set up a zero coupon bond, which is a fancy name for a loan. And let's suppose that Shruti is making a loan to Charles. She's the investor, he's the issuer of the bond. And Charles wants to borrow 1 ADA from Shruti. and he's promised to pay back 1.1 ADA. So we've set it up, we've said who the issuer and investor are, we've said what the price and the eventual value will be, and we're now going to create the contract. In order to do that, we have to make a payment of 30 Lovelace to get the contract started. So let's pay, and we're asked to approve that, and the payment goes through. And you can see now in Shruti's Marlowe run, we've got the zero coupon bond running. But also, if you look at Charles's view of the world, it's running there too for him. Let's see what it looks like for him. We're at the first step, and it's saying it's waiting for something from the investor, who is Shruti. So let's see what's happening in her view. Yes, she's asked to make a deposit, so let's click on that to make the deposit, and click to confirm with a fee of 10 Lovelace, and make that deposit. And then you can see her view has changed. Now she's waiting for the issuer to pay her back. And hey ho, we look in Charles's view, which is incidentally the mobile view of Marlowe Run. He's asked to pay his 1.1 ADA. Let's make him do that now. And he'll also have to pay a 10 Lovelace transaction fee. And let's make that deposit. And you see now from both their perspectives, that loan is completed. You can see the history of what's gone on. You can see at particular points the balances that the contract holds. And in fact, we can, if we close that, we can see the history of all the contracts that that Shruti has taken part in. So I think that pretty much covers the basics of what you get from Marlowe Run. It's a intuitive interface to a contract running on the blockchain, and you see that each participant in the contract gets their view of the contract in real time, updated from what's, in this case in the browser, but eventually what's on the blockchain. Okay, so that's given you an idea about what Marlowe Run looks like, and let's now take a look under the hood and see how it is that Marlowe will be executed on Cardano. Well, here's a diagram just to give you the context. I'm sure you understand most parts of this diagram already. We have a Cardano node on which Plutus is running, and as you know, Plutus is a dialect of Haskell, more or less. Now, Marlowe is embedded in Haskell, and Marlowe compiles, is executed using Plutus. So Marlowe sits on top of Plutus, but it's also linked to, through Marlowe Run and attachment to a wallet. You'll be able to interact with, as an end user, with a running Marlowe contract, and also it gets linked to oracles and so on sitting out there in the real world. Now, what does it mean to execute a Marlowe contract? Again, I think this will be familiar to you from your work with Plutus, but let's just talk through precisely how it works. Executing a Marlowe contract will produce a series of transactions on the blockchain. And obviously what Plutus running on Cardano checks the validity of transactions. We have a validation function. And what the validation function for these Marlowe transactions is, essentially, is a Marlowe interpreter. It checks that the transactions indeed conform to the steps of executing the Marlowe contract. And that's done using the EUTXO model. So we pass the current state of the contract and some other information through as datum. So the Marlowe interpreter uses that to ensure that the transactions that are submitted meet the criteria for the particular Marlowe contract. So that's the on-chain part. Now obviously off-chain, there's a component as well. So we have to have Marlowe Run. We'll have to build the transactions that meet the validation step on chain. And if and when the contract requires crypto assets, we will have off-chain to ensure that transactions are appropriately signed, so that we will have authorization for spending crypto assets effectively. So using Marlowe Run and an associated wallet, we construct the transactions. And we get a flow of information in both directions. Marlowe Run will submit transactions to the blockchain that then can be checked, validated by the Marlowe interpreter, which is itself a Plutus contract. It's one of the largest Plutus contracts that exists. But there's also information flow another way, because suppose that the transaction I've submitted is a deposit of money into a running contract. And suppose the contract also involves Charles Hoskinson. So my instance of Marlowe Run has submitted that transaction, but Charles has also to be notified about that. And the information flows in the other direction, using the companion contract, to ensure that every instance of this client, the Marlowe Run, gets informed about activity in that contract. Now, Alex will talk some more about the details of the implementation, but here you're seeing an outline of how it all works. Transactions are validated online through the interpreter, but they have to be built offline, and in some cases have to be authorized. And we use, essentially, the blockchain is the central synchronization point for the distributed system that is the collection of instances of Marlowe Run that are interacting to make the contract, to execute the contract. And you saw in the demo just before that we could see in those two separate windows we were sharing information. Now that was simulating it locally, but in production this will be information that's stored on the blockchain. Okay. Now let's talk a little bit about how the system is designed in a high level way. Here's a piece of the semantics of Marlowe, and as you can see, it's a Haskell function. We take an environment, a current state, take a contract to be executed, and based on what contract that is it a close, is it a pay, we can take some steps of computing the results of that contract. And we do that in a way that uses Haskell in a quite straightforward way to advance the contract. And what we have is that this specification in Haskell is an executable specification of the semantics. And this gives us some very nice consequences. We've got, if you like, we've got the denotational, we've got a high-level description of what the semantics is, and we're doing that through something that is effectively an interpreter. So we're defining at a high level this interpreter, which is an interpreter in Haskell for Marlowe contracts. Now, one really nice thing about writing it in this sort of way is that we can be sure we cover all cases, because it's it will be obvious if we're missing some cases. Writing it as something that's an interpreter ensures that we will hit all cases we need to in describing the semantics. And also, it really helps us to understand the semantics. So this was it's a really, when you're designing a language, okay, you have an abstract idea about how you're going to, what it's going to mean, but there's nothing like having an implementation of it so you can actually run the semantics. You say, well, what would it mean if we were to add this construct? What would it mean if we were to modify the semantics in this way? Now, if you'd written it in a purely logical format, it's difficult to unscramble just from the rules as they're laid out what precisely a change in rule might mean. Here it's straightforward, we can run the semantics. So we've got this specification in Haskell. And what's even nicer is that we can reuse this semantics in a number of different ways. So in the theorem proof at Isabelle, we can use the semantics for reasoning and proof. And we use pretty much the same semantics, because Isabelle uses a functional language as its subject. We can run the semantics in Plutus. It was written in Haskell initially, but Plutus is more or less Haskell. Perhaps not with all the libraries, but we can, in principle at least, build our implementation on blockchain from our semantics. And also we can translate the semantics into PureScript for simulation in the browser. Now, PureScript is not exactly the same as Haskell. Isabelle's language is not exactly the same as Haskell. How can we be sure that all these versions are the same? Well, one way of doing it is to extract Haskell code from Isabelle and test the original against this extracted code. And we do that on random contracts. And that gives us a pretty high level of assurance that the two are the same. And down the line in our roadmap, we certainly expect to be using a Haskell in JavaScript implementation at some point to replace PureScript in the front end. So we don't have to write a PureScript version of the semantics. When we're doing the off-chain interpretation, building the transactions to be submitted, we can use the actual real Haskell implementation by coding it, compiling it into JavaScript and running that in Marlowe Run, in the client code. So building the language in Haskell has given us these consequences that though we use various different versions of the semantics, we can get a high level of assurance that these are the same. And indeed, we can, in some situations, replace things like the JavaScript by the PureScript by JavaScript. Okay, so that gives us a picture about how the system is put together. Let's go to another aspect of Marlowe, which I talked about it being a special purpose language, about it being a DSL, and that promoted usability. Let me say a bit more about that. One way we promote usability is that we provide different ways of writing contracts, different ways of authoring contracts. And another way we promote usability is to allow people to explore interactively how contracts behave before they're actually run in a simulation. So let's talk about those now. Again, emphasizing these are another facet of assurance for the language. We want to write a Marlowe contract. How can we do it? Well, we can write Haskell, the Haskell Marlowe data type as text. That's one way we can do it, and that's fine. And we have an editor for that inside the playground that gives that has completion, that has holes which will support completions, will make suggestions, and so on. So we can build Marlowe contracts as pure Marlowe. But there are other routes as well. We have a visual editor for Marlowe so that you can produce Marlowe contracts visually with putting together blocks, so in a way that doesn't require you to be a confident programmer. You can start off by using the visual version as a way of learning Marlowe, as a way of engaging with it. If you are a coder, perhaps in Haskell, perhaps in JavaScript, Marlowe is embedded in Haskell and in JavaScript. So we can use facilities in Haskell, like recursion or JavaScript, to describe Marlowe contracts. So we can say in Haskell, let's, we want to do this particular pattern of behavior n times. And we can write that in Haskell. And then for a particular contract, we convert the Haskell into Marlowe. We, as it were, compile this Haskell description of a Marlowe contract into pure Marlowe. And we can also do that for JavaScript. So we have that facility. And then finally, something I'm not going to talk about anymore in this talk is that we can generate contracts from initial conditions, and we've been looking at that for the ACTA standard of financial contracts. So we generate, on the basis of the contract terms, we generate code in Marlowe. So we write functions whose output is Marlowe code. So we provide users with, as well as simply writing pure Marlowe, we provide them with a variety of different approaches. Leveraging knowledge of JavaScript, for example, or leveraging a non-code-based approach for describing the contracts. And also we allow people to simulate the behavior of contracts. Now, this is something that you can see in the current version of the Marlowe Playground. I've taken a screenshot of that. That's something you can play with yourselves. What I would say is that we are looking at different ways of describing the results of a simulation. So at the moment we have a transaction log. We are allowed to choose an action, the next action to perform. You can perform that. You can undo the last step to take you back, and then try another path. So you can step interactively backwards and forwards through the source code, through the application of the contract. What we're looking at is changing the user interface, changing the UX for the Marlowe Playground, Marlowe Play, so that we'll use something rather more like the Marlowe Run description of a running contract, so that you'll see the steps as a series of cards like this. But that's work in progress. Okay, so we've talked about usability. What about the sort of assurance that Marlowe can give users? There are two apart from the things we've seen already. We've seen that making the system transparent, making code readable, is itself an advantage. We've seen that there's simulation to give people the ability to understand, to validate their intuition about a contract. But rather more formally, we can use the power of logic to do two things for us. We can do what's called static analysis, so we can automatically verify properties of individual contracts. So that means we can guarantee this contract will behave as it should, checking every route through the contract. And also we can do machine-supported proof, so not automatic any longer, written by a user, but we can prove properties of the overall system. And let's talk about those two now. What about static analysis? Well, what static analysis allows us to do is check all execution paths through a Marlowe contract, all choices of slots for a submission of a transaction. So every possible way in which the contract might be executed, we examine. And the canonical example here is the example of whether a pay construct might fail. Is it possible a pay construct could fail? And the answer is that we use what's called an SMT solver. It's an automatic logic tool, a powerful logic tool called Z3. It's the one we use, others are available. That effectively checks all execution paths. And what it does is if the property is satisfied, that's fine. We get the result, yes, it's satisfied. If it's not satisfied, we get a counterexample. We get told, here's a way, here's a path through this contract that leads to a failed payment, a payment that can't be fulfilled. So here's an example of how it can go wrong. And that's really helpful because it means that you can debug. If you don't, if you really want to make sure that failed payment can't happen, then this gives you a mechanism to understand and to debug how that eventuality happens, and so gives you a chance to think about how to avoid it. So very powerful and entirely push button. You push a button and you get the results. And here you can see, just again to emphasize these, here's the assurance. We can do this high level check through all execution paths. So here you see a fragment of a Marlowe contract. It's an escrow contract where the contract starts with a deposit of 450 Lovelace. And checking the analysis in the playground, we've got the result. Static analysis could not find any execution that results in any warning. So that's saying you're okay. It's not going to give you a warning whatever you do. But if we change that deposit of 450 Lovelace to a deposit of 40 and analyse, we then get this warning. We get a transaction partial payment. And we're told we get to a payment where we're meant to pay 450 units of Ada, that is Lovelace, but there are only 40 available. And we get given a list of transactions that take us there. So we're able to see from that how we got to that. And the problem is that we didn't put enough money in, and then we reached a place where we needed to make a payment of 450. So it's easy for us to see that we need to either make the payment smaller or the initial deposit bigger. But it's entirely push button. So we do get that sort of assurance for free, as it were. But thinking about verification, we can do rather more than that. We can prove properties of the system once and for all. So for example, just looking on the left-hand side here, we can prove that accounts, local accounts inside a Marlowe contract, as it executes, we can prove from the semantics that these accounts never go negative. You can't ever overdraw an account in a Marlowe contract. And we can also prove this theorem of money preservation. We can prove that if we look at all the money that's gone into the contract so far, that's equal to the sum of two things. The amount of money that's in the accounts held inside the contract, plus the amount of money that has been paid out. And that gives a clear picture of money preservation. So we're able to write proofs of these very general properties of the system. Now we're also able to prove other more technical things about the system. So for example, that a close construct will never produce any warnings. So if we're analysing for warnings, we don't need to worry about close constructs. So that allows us to optimise the static analysis. And we're also able to prove that the static analysis, the way it works, which makes a number of simplifications to speed things up, is sound and complete. That means the static analysis will give us an error warning when the real contract can generate an error warning, and it won't give us an error warning if the real contract can't do that. And one thing that we haven't done, but is again on our roadmap, is we can do these sorts of proofs for individual contracts or individual contract templates too. Things that we can't necessarily prove with static analysis, we can prove by proving them by hand. So high-level assurance we get, if you're prepared to write proofs, the system is amenable to having these proofs written about it, and they give us the highest level of assurance about how it works. So I think I've said enough for the moment about Marlowe. Where can you go to find out more? Well, there's a Marlowe GitHub repository that has the semantics and the basics about Marlowe. Quite a lot of the implementation of the tools for Marlowe are in the Plutus repository, because it has that repository as a dependency. So we include it in that repository. So that's where you can find the code itself. If you look in the IOHK online research library and search for Marlowe, you'll find a number of research papers we've written about how the system works. You'll also find an online tutorial in the Marlowe Playground. And finally, Alex is going to give some more information in his presentation coming up next. So just to summarise, what we have in Marlowe is a DSL, a special purpose language for financial contracts, running on top of Plutus. And because it's a DSL, it gives us assurance. It allows us to give assurance that it's harder to give for a general purpose language. And also it allows us to orient its design around users as well as developers. And also that we get assurance of contracts behave as they should and don't do what they shouldn't. Some of that is built into the way that the language is designed. The language is simple and therefore we get readability. We also get simulatability and we get these stronger assurances of static analysis and verification. So, okay, thanks very much for listening, and here's the link to go and see the Marlowe Playground in action. Thanks very much.
Hello, my name is Alex Nemish. I'm one of the Marlowe developers, and today I'm gonna show you a bit of Marlowe semantics and part of PAB contracts, Marlowe PAB contracts that we are going to use. I'll start with a brief description of Marlowe semantics that's implemented in this semantics.hs file, and then I'll show you the PAB contracts. I assume you're familiar with Haskell, you're familiar with Marlowe semantics in a high level, and I expect you to see the Lars presentations. So I expect you to know how PAB works in a nutshell, and how state machine library works, and state machine library based contracts. Let's get started. Here are the main data types for Marlowe. It's a contract. Essentially, those are 6 constructors that you construct Marlowe contract with. And here's the state that is going to be stored on a blockchain. So we have a state of balances of accounts by party. Here we store the choices parties made. Here we store bound variables that are essentially led bindings. And here is mean slot is essentially a first slot that the contract sees, and this just to prevent to go back in time. The input data type contains essentially actions for Marlowe contract. It's either deposit or choice or a notification of a slot change. And here is the transaction input data type. That's what we give as an input. So we have a slot interval. So every transaction must have a defined slot interval, and the list of inputs. So you can combine multiple inputs within a single transactions. You can make multiple deposits or choices and notifications. And we get a transaction output which contains the payments that we expect to happen, the output state and the output contract, resulting state and resulting contract. Here's the Marlowe data. That's essentially what's going to be stored on a blockchain. So it's a current state of a contract and the actual contract. So the main function, the main entrance to the semantics is a compute transaction function that that gets transaction inputs, current state, current contract, and gives the transaction output. So first of all, we fix the interval, we check the slot interval for errors. For example, we disallow slot interval to contain any timeouts inside. So for example, if we have a contract with a when construct with a slot 10, for example, you cannot produce a transaction that has a slot interval from 5 to 15, because it's going to contain a timeout inside of it. It's going to be invalid slot interval. So here we check this. Then we apply all inputs. If it's successful, we return the transaction output with warnings we found, the payments we expect, new state, and a continuation. So what happens in apply all inputs? Essentially, it's a loop that first of all reduces current contract until it's quiescent. And then, when we get this quiescent state, we take first input and try to apply it until we get apply it and essentially continue with this loop if it's applied successfully until we get an empty input list. Then we return current state and continuation. Reduce contract until quiescent is essentially a function that again goes through a loop and tries to apply reduce contract step function, which essentially evaluates a contract. So if we get a close, then we are in a quiescent state. If we get a payment, we evaluate value, update balances, and return that the contract was reduced. We do the same with if, let, and assert, but for when, we only evaluate it if it's timed out. Otherwise, we say it's not reduced. So when we get this not reduced, then we say that the contract is quiescent. So in a nutshell, Marlowe contract evaluation consists of two steps. We reduce current contract until it's quiescent, so essentially it's either closed or we get to a when that's not timed out yet. And the second part, we try to apply inputs and evaluate the contract further. Okay? Let's see how it works from the client side. As you may have noticed, the Marlowe semantics code is quite abstract and it does not depend on the Cardano nuances, transactions and stuff. So let's take a look at the actual Marlowe validator that's been executed on chain. So here's the script instance that essentially just calls this make Marlowe validator code that uses a state machine library make state machine call and provides a two functions, state transition function and finality check for a state machine. So finality check is very simple. We just check that current contract is closed, then the state machine is done, and the state machine transition function is the actual meat of the validator. So it receives a Marlowe params data type. We're going to talk a bit later. Current state of a state machine, Marlowe data. Marlowe input, this is essentially a transaction input expressed in Cardano types, and it's going to return either nothing in case of an error, or a set of transaction constraints that must apply to validate a transaction, and a new state, a new Marlowe data, a continuation contract, and an updated state. So here we check that the balances are valid. So we require balances in a state to be positive. Here we produce an input constraints given these inputs. So in case of deposits, we expect money go into a contract. In case of choices, we expect signatures or witnesses of respective parties. We calculate the total balance that the contract claims it contains, and we check that it actually contains these values. We construct a transaction input given the slot interval and list of inputs, and we call the compute transaction functions that we saw in semantics.hs. And we, given a computed result, we construct a new Marlowe data with a new contract continuation and updated state, and produce an output constraints that contain payouts to respective parties. And we calculate new balance, new total balance, given the income and outcome of a transaction and inputs, and we combine all those constraints with range validation. While validating inputs, we check that there are signatures from parties presented by public key hashes, and there is a spending of role tokens for parties that represented by a role. Payments to parties go either by checking that there is a transaction output that goes to a public key for parties that presented by public key hashes, or the payment goes to role payout validator hash. That is a custom validator that you can provide on your own within Marlowe params, or we have a default one. This is a role payout validator that is used by default. That it simply checks that a transaction contains a spending of a role token given a currency. For off-chain execution, we provide 3 Marlowe PEB contracts: Marlowe follower contract, Marlowe control contract, and Marlowe companion contract. Let's go through all of those. Let's start with Marlowe follower contract. It's a very simple one. It contains only one endpoint called follow, and it basically subscribes to a validator address, a Marlowe contract address essentially, and it subscribes to all changes to this address, so we get all the transactions that spend the spend transaction output with this Marlowe contract. So we can store all the inputs that are applied to a Marlowe contract. So here you can see that we call this update history from transaction that in a nutshell finds an input, Marlowe inputs in the transaction, and if it finds it, it constructs a transaction input data type and update the PAB contract state with this transition. So if you're connected to a WebSocket of this contract, you will be notified about state transition changes. And this state of this contract, called contract history, it's essentially stores an initial Marlowe params, initial Marlowe data, and the list of all transaction inputs that were applied to this contract. And you can always restore the latest state by applying a list of transaction inputs to an initial state. This contract is used by Marlowe run to show a Marlowe contract execution history, and you can use it for the same purposes on your own. This Marlowe Plutus contract is essentially a control contract. It allows you to create a Marlowe contract, an instance of Marlowe contract, apply inputs to the instance, auto-execute the contract if it's possible, redeem tokens from payments to roles, to your role, by spending transaction output protected by role payout validator script, or just close this contract. Let's go through Marlowe contract creation. So when you're calling the create endpoint, you provide an actual Marlowe contract to be created and a map of roles to public keys of role token owners. So what happens here is we need to set up a Marlowe params. Let's take a look at this data type. So Marlowe params is a way to parameterize a Marlowe contract in the following way. You can specify your own role payout validator by providing its hash. So you can write anything you want. We have a default one that checks that the role token is spent within transaction, but you can do whatever you like, and you can do this by specifying this hash in Marlowe params. Also, when your contract uses roles, we need to know a currency symbol of role currency. So you specify it here. So when we create a new contract that uses roles as parties, we need to create a new currency and distribute role tokens to their owners. That's why we need this map of role tokens to their owners. So let's take a look at the setup Marlowe params function. So what happens here, we get roles that are used within this contract, and if we have roles and we have owners all provided for these roles, we create tokens with role names. By default we create a 1 token per role. Then we use this forge contract function. That's essentially we reusing other PAB contracts. This one is from currency contract that creates a new currency, and all these tokens go to the creator. So whoever creates a Marlowe contract initially gets all the roles for this contract, but we get role symbol from that, and we immediately within the same transaction same transaction that creates Marlowe contract, we distribute role tokens to their owners. So we give them to respective parties. And we create Marlowe params that contains the role symbol, currency symbol of currency we just created for role tokens. Currently we use the default role payout validator hash. So this is a set of constraints that create new currency and distribute role tokens and create transaction output with the Marlowe data. So we use state machine library to create state machine client, and we construct a transaction that distribute tokens and create a transaction output with the Marlowe data and pay value. This is a deposit value. Currently it's 0, but at later point it's going to be some value. I believe it's going to be 1 ADA. All transaction outputs must contain some ADA in it, just to essentially it's preventing the DDoS attacks. And we submit this transaction. That's the way we create a Marlowe contract on chain. Apply endpoint is very simple. Apply inputs endpoint. Just call this apply inputs, which is very straightforward. We construct a slot range, and we use state machine library run step to run a state machine transition function. And we provide Marlowe input, which is a pair of slot range and list of Marlowe inputs, list of inputs. Redeem endpoint allows you to get money from that's been paid to a role payout script. So we get this address given a role's currency, and spend all these outputs to a token owner. Auto is quite interesting, though complicated thing. There is a set of contracts that can be executed automatically. Imagine any contract that contains only deposits and payouts. So if this contract is eligible, so no participant needs to provide choices or any like interactive stuff. So only scheduled payments. These contracts can be executed automatically, and this endpoint allows exactly that. So if the contract can be executed automatically for a party, we call auto-execute contract. This is essentially a state machine that pays deposit or wait for other parties to do their part. The last interesting contract is Marlowe Companion contract. This is a contract that monitors a participant wallet and notifies when a role token goes to your own address. So it runs, it listens to transactions that go to your own address, and if there is a token and this token is generated by Marlowe contract creation, it tries to find the Marlowe contract, and if it succeeds, it notifies this contract, it updates its state, and again, if you're subscribed to this contract WebSocket, you get a notification about a role token, and you'll get Marlowe params and Marlowe data. So if you check this Marlowe companion state, this is essentially a map of Marlowe params to Marlowe data. So you can always get notified about receiving a role token. Hope this helps. Thank you very much for listening.
Thank you very much, Simon and Alex, for these very nice introductions and explanations to Marlowe. And I thought it would be nice if we play a bit with Marlowe in the playground. And when you go to the playground, by the way, I went to a different version than the one Simon showed in his lecture on his slides, because there was a problem with that one right now, but this one works. So it's alpha.marlowe.iohkdev.io. And when you go there, you first get presented with 3 options in which language you want to write your Marlowe contracts. So you can do it in Haskell, you can do it in JavaScript, or you can do it in Blockly or directly in Marlowe. So let's first look at this option, because this is very nice and you don't need any programming experience to do this. So I start a new project and pick Blockly. This is a graphical editor, so we can just click and drop a Marlowe contract together. And as an example, I want to write a contract where there are 3 parties, Alice, Bob, and Charlie. And the idea is that Alice and Bob deposit an amount of ADA into the contract, let's say 10 ADA. And then Charlie decides whether Alice or Bob gets the total amount. And depending on Charlie's decision, either Alice gets 20 or Bob gets 20. And of course, there's always the possibility that one of the 3 doesn't play along. And Alice doesn't make her deposit, Bob doesn't make his deposit, or Charlie doesn't make his choice. In which case, everybody should just get reimbursed what they have paid up to that point. So when we start with Blockly, there is a contract, and it's just a close contract, which in this case doesn't do anything. If there was money in internal accounts, it would pay back the money to the owners of the accounts. But we want to do something else. So let's first wait for a deposit by Alice. And because that's an external action that's triggered by one of the parties, in this case Alice, we need this when construct that Simon mentioned. And we can slide that into here, and we see all the slots where other things need to go, and we see some fields that we have to set. So let's start here. So we can set a timeout. So let's say this deposit by Alice has to happen until slot 10. And if it doesn't happen, we can say what should happen afterwards. And there's not really a good choice to do anything except close in that case. So in that case, nothing will happen. So we can slide that in there. So now here we say what external actions we wait for. Let's say we only wait for one action, namely that Alice makes her deposit. So we can check for actions and pick the deposit one and slide it in here. And we see a couple of slots we have to fill. First of all, who has to make the deposit? That's a party. And there are 2 choices, public key or role. Let's take role, because then I can just say Alice. Normally this would be the name of the role token. So whoever owns that token can incorporate that role. Okay, so Alice makes a deposit. Now the amount, that's a value. And let's say we just pick a constant amount of 10 ADA. So amount is 10, and that it is ADA we must specify here in the currency slot. There's also the option to use other tokens than ADA, but let's stick with ADA. Okay, now there are these internal accounts that also belong to one of the parties. So let's say Alice pays it into her own internal account. So I just copy pasted this. And now we must say what happens next if Alice makes this deposit. So afterwards we want Bob to make a deposit. So I can just copy this whole when block here and slide it in here and now change it. So first of all I change the timeout to 20. So to give Bob also 10 slots to do something. And then wherever I set Alice, I now say Bob. So at this point, if both these actions happen, Alice has deposited 10 into her internal account and Bob has deposited 10 into his internal account. So now we want Charlie to make a choice. So we need, this is again an external action. So again, we need a when. And I put that in here, but this time it's not a deposit. So let me delete the deposit, but let's change the timeout to 30 to give Charlie 10 slots to make his choice. And now I need a different action where earlier I had deposit. Now I pick the choice action. I can give it a name, let's say winner. I must say who makes the choice, so that's supposed to be Charlie. And now I must specify what values this choice can have. And that's numeric, so somehow, because Charlie is supposed to choose between Alice and Bob, so that's two choices. So I can pick arbitrary values like 1 and 2. 1 for Alice, 2 for Bob. So, and that's already the default, so that's fine. So this allows Charlie to only choose 1 or 2. And then after he has made the choice, if he has made the choice, we continue. And now it depends, of course, on what choice Charlie has made. If he chose Alice, then Alice must get all the money. If he chose Bob, then Bob must get all the money. So here in this continue contract, we now can use if, simple conditional, slide that in here. So first we need the observation. So we must somehow check whether the choice was, let's say, 1 for Alice. So this is an observation, and there is value equality is one of the options. So we want to compare the choice that Charlie made with 1 or 2, doesn't matter, but let's say 1. So value, there is this one, which gives us the value of a choice. So here we need the name again. So winner was our name for that choice, because there can be several choices, so we must be able to distinguish between them. And we again need who made that choice. So this is now either 1 or 2, and we can compare to, for example, 1. So we can use the constant value 1. Okay, and in this case, so if this is true, then Charlie chose Alice. So we want Alice to get all the money. So in the then branch, we can now take a pay contract. The payee is who gets the money. And now we have two choices. That can be an internal account or it can be an external party. And in this case, it doesn't matter, because in the end, when we close, all the parties get the money from the internal accounts as well. So it doesn't matter. I can just pick the internal account, Alice's internal account. So let's do that. Pick Alice. So this now means that the payee is Alice's internal account. Now how much? That's this constant 10, the amount that Bob paid in. Currency is ADA. And now who pays? And that must be an internal account, because this is something this pay contract is something the contract has control over. So that's not an external action. So payments are triggered from internal accounts that are under the control of the contract. And that in this case is Bob's account. So this now says if Charlie picked 1, which stands for Alice, then pay from Bob's internal account 10 ADA to Alice's internal account. And afterwards, we can just close. And when we close, all the internal accounts will be paid to the external owners. So at this point, Alice's internal account will have 20 ADA, and when we close, she will get the 20 ADA paid out. Okay, and else, this is now if Charlie didn't choose Alice, if he chose Bob, well, then we must do the same, but with reversed roles. So let me copy paste this whole pay thing and just exchange Bob and Alice. And this should do it. Now we can, for example, look at the pure Marlowe. So this is now the value, what I did graphically as a Marlowe value, a value of the Haskell data type called Marlowe, or called contract actually. And I can send it to the simulator. And I can start the simulation. And now whenever there is a when, so when there are available actions, I get prompted which of those to take. In our case, we always only had one available action at every point. So in the first when, there are only two possibilities. Either Alice makes her deposit or she doesn't until the timeout is reached. So in this case, if we wait for the timeout, it's very boring. The contract is over, is reduced to close, and nothing happened. So if she makes the deposit, then this contract simplifies. So it's now reduced to what happens after she made the deposit. And we see now we are in the second when, where we are waiting for Bob's deposit. And again, he can choose not to deposit. So if he does that, then we see here the actions. Alice deposited 10. And then after the timeout, because Bob didn't do anything, the contract paid 10 back to Alice. Okay, of course, it's more interesting if Bob also makes his deposit. So we see that logged here as well. And now the contract has simplified again. So now we are in the when where the only available action is that Charlie chooses. So Charlie can now choose one or two. If he chooses or, don't do anything. If he doesn't do anything, Bob and Alice both get their money back. If he picks Alice, so choice 1, then we see that the contract pays 20 units of ADA to Alice. So she gets all the money. And if instead we pick 2, then the contract pays 20 units to Bob. So it seems to work. Let me reset this now. And let me copy this Marlowe contract and do a new project and go to the Haskell editor instead. And let's not save. And here in this Haskell editor, there's a template. Basically, all this Haskell program does is it takes a contract. This is a Marlowe contract. And then it's a simple executable, a Haskell executable that just pretty prints the contract. So all it does is it basically produces a nicely printed value of type contract. And this is then used to, for example, run in the simulator. So we should be able to simply, instead of close, paste this expression here that we got from our Blockly. Probably I should indent. Okay, and that should compile, so I can compile this. And I can send it to the simulator, and it should behave exactly as before. So Alice makes a deposit, Bob makes his deposit. Let's say Charlie picks Bob, and Bob gets the money. So there we don't really see a benefit of doing it in Haskell. We could just as well do it in Blockly. Although I find that Blockly is really only useful for learning and for writing extremely simple contracts. Because this is arguably a simple contract, and already it was quite unwieldy in the Blockly editor. And if you do something slightly more complicated, it gets really very confusing in the editor. But the point is, we can do other things in this Haskell program as well. We don't have to literally define a contract. We can use the whole power of Haskell to help us write this contract. So for example, we see there's lots of repetition because we always have these roles Alice, Bob, and Charlie. So for example, we can define them separately and just say Alice, Bob, Charlie. The type is party, and the role constructor, we can just use this overloaded string here to skip the role constructor and just write it like this. So party implements isString, and the fromString method uses the role constructor. Charlie. Okay. And now I can replace this everywhere with those. Here as well. And here as well. And I can do the same for Bob and Charlie. Okay, I think I have all the places. Now I can do the same. This constant 10 is all over the place. So let's give that a name as well. Let's call it deposit, and that's of type value. Okay. This token empty empty, there's the ADA abbreviation for that. Okay, and there's slightly more computation duplication, this choice ID. So let's also give that a name. Choice ID, type choice ID. And that takes two parameters, the name, which was winner in our case, and the role, which is Charlie. Okay, now it's already cleaned up quite a bit. And now it's also easy to do more sophisticated things. For example, our contract is slightly asymmetric, even though it sounds like a symmetric situation. I mean, Alice and Bob are completely symmetric, but in our contract, Alice has to deposit first. And what we could do instead is allow Bob to deposit first as well. So in the outermost when, we have two cases, one where Alice deposits and one where Bob deposits. So we can, of course, just now copy this case here and paste it below and change Alice and Bob where appropriate, which is not everywhere, because in this choice thing here, Alice keeps being choice 1 and Bob keeps being choice 2. So would have to concentrate on that. But of course, it's much nicer to extract that into a helper function. So this is of type case. So let me just copy paste or copy this until there. And now make a local definition. And I don't know what to call it. Let's just call it F. And it takes two parties, the party that deposits first and the party that deposits afterwards, and it gives us a case. Let's call it X and Y and just paste this whole thing there. Okay, and now of course I am not using the X and Y, so in this case Alice was first. So Alice is X, and after Alice's deposit we wait for Bob. Okay, and this here can stay the same, this choice. Okay, and now I can replace this whole thing with my helper function and write F Alice Bob. And the advantage is that it's now easy to also add the symmetric case that Bob can deposit first. So I just add a new line with another case, Bob Alice. And if all goes well, that should still compile. And if I now send it to the simulator and start the simulation, now I have two possible actions that can happen in the first step. Alice can deposit 10 or Bob can deposit 10. So let's Bob start this time. So Bob deposits 10. And now it's Alice's turn. And if Charlie picks Alice, then as before, Alice wins. So the point I'm making is that it's of a big advantage to use the Haskell editor to write Marlowe contracts in Haskell. So basically you write a program that produces something of type contract. And you can use all the features of Haskell, like local functions or whatever, to make your life easier and avoid code duplication. And in the Blockly editor, there's no such option. If we had wanted to do the same in Blockly, because there are no local definitions that you can do, you can't define local contracts or something like that. So we would have to copy paste this whole big case and then manually change Alice to Bob and Bob to Alice in the first two deposits. And we would have lots of code duplication because this choice thing here, the third when, would have been copy pasted and there would have been no way to abstract that away and only write it once. And of course you have other options. For example, we could also parameterize our contract. So for example, we could use leave the deposit variable. So we could instead do contract is a function from value to contract. And the first parameter is deposit. And I delete this here. And now in the main program, I can pick a value for the parameter, for example, 50. And now if I compile, oh, sorry, it must be constant 50. So now if I compile, I have a version of the contract where now Alice and Bob have to deposit 50 ADA each. And then the winner gets 100. And obviously I could do the same for the parties. So I could parameterize it over the three parties. Party, party, party. And then if I call those Alice, Bob, and Charlie, delete this here. Then I must also be careful, and this must now depend on a party. Let's call it P. And at the appropriate spot here where the choice happens, I must say choice ID, Charlie, here as well. Okay, and now the contract is parameterized by all participants. So instead of Alice, Bob, and Charlie, I can use Charles, Simon, and Alex, and constant 100. What did I do now? Oh yes, just a parenthesis problem. Okay. And now I have Charles and Simon and deposits of 100. And Alex picks the winner. And it works as before. So it's very nice and easy to using Haskell, parameterizing contracts and saving a lot of code duplication by just using usual Haskell features like local definitions, helper functions, and so on. I could even relatively easily generalize this to more than 3 participants. Maybe there are 3 people. I could even write a contract that's generic in the number of parties. So I get a list of parties and then each of them has to deposit. And that would be very inconvenient if I had to do that by hand. But just using Haskell, it's quite straightforward. And what is also noteworthy here is that Marlowe, in contrast to Plutus, is extremely basic Haskell. So the Marlowe team made a point of only using very basic Haskell functions and features. So you don't need lenses, you don't need template Haskell, you don't even need monads. Type level programming, all of that is not present in Marlowe. It's extremely basic standard Haskell. So after what you have learned while learning Plutus about Haskell, Marlowe should be a walk in the park for you, and very relaxing and simple. Of course, Marlowe is not always appropriate because it's specifically for financial contracts, but if it is appropriate, it's a very nice option because of all the safety assurances that Simon mentioned, and because it's much simpler and easier to get right than Plutus. For homework, I would like you to modify the contract that I wrote as follows. Charlie should put down a deposit in the very beginning of twice the deposit that Alice and Bob put down. And if he then doesn't choose, when it's his turn to choose, Alice and Bob get half of what he put down. So Alice and Bob each end up with 20 in this example. So in the very beginning, Charlie is supposed to put down 20. Then it proceeds as usual. So if all goes well, Alice and Bob both put down 10 and Charlie makes his choice. For example, for Alice, then as before, Alice gets the 20 and Charlie gets his original deposit back. But if Charlie does not make a choice and the deadline is reached, then his 20 are split amongst Alice and Bob, so Alice and Bob both end up with 20.